Okay, so I updated that handout on week 5 where we figured out the gate resistance, the drain resistance, source resistance, base collector for the quick method. I updated a little bit, and what I updated was for GM, big GM is just little GM for every circuit except for circuits that are degenerated. And there's 4 circuits that you consider degenerated. There's the common emitter with degeneration. There's the common base with degeneration. And it's weird because the input is on the emitter, and that resistor goes in the same place as the common emitter. But now the input is on the other side of your degeneration resistor. So those are the BJT versions. And then there's the MOSFET version, which is the common source with degeneration. And then the same thing, the common gate with a resistor on the source in between the V-in and the transistor. So all of those are considered to have degeneration. And the equation for GM then, so for every other amplifier you've seen, big GM is just little GM, plus or minus little GM. But for these, your GM is decreased by 1 plus GM times RE. And again, if it's a common emitter, there's a minus sign in front. If it's a common base, then there's no minus sign in front. So the 2 amplifiers on the left, those are common emitter, common source. They're inverting, so you need a minus sign. The common base and the common gate, those aren't inverting, so you wouldn't need a minus sign. And I posted that up on week 7. That's just an updated version of the week 5 handout. Okay. Then the other thing that I added, there was a request to have just the basic version of all the amplifiers, single transistor amplifiers in one place. So I put that on the handout too. So this should help you with the quick method. Yeah, I don't think I changed anything else. Any questions on that handout? Okay, so that is up. But let me go mute my mail. So just for, let's see, I'll do this one. Okay. So that's week 5 handout. And since the homework, let's say if you can get it in Wednesday night, by Wednesday night or something, that'll be good. That'll be in time for the graders to get to it and all that good stuff. So on that homework, there were a couple of things that I didn't talk about, and I apologize yet again. And one is the common mode gain. So ACM is your common mode gain. And two metrics. And metrics are things that help you say a lot about a circuit by just saying one thing. So if you said my power supply rejection ratio is 1,000, that gives a lot of information to somebody about your circuit. Okay. It's just like if you say, hey, my amplifier has a gain of 20, that gives a lot of information about your amplifier, and you don't have to say, when I change V in by 1 volt, V out changes by 20 volts. You don't have to say that whole thing. You just say, hey, my gain's 20, and they already know that. So it's kind of a shorthand for giving a lot of information with just a single number. So let's look at ACM first, and I believe I did the experimental. So again, experimental means if you're using LT Spice or in the lab, how you would find this value. And I think we already did that, but So let's do a quick example of that. Again, I drew BJTs here, but MOSFETs work just as well. And in lab, you tied V in plus equal to V in minus. And if you remember, VIC, that's just the average. So it's VI plus VI minus over 2. Okay. If you tie VI plus to VI minus, that means VI plus equals VI minus. And what's your average?
VI plus.
Yeah, it could be VI plus, which also equals VI minus. So you already have your average. If you just look at the value on the base, you already have your value for VIC. So it's kind of a convenience thing when you're doing the common mode gain that you tie the two inputs together. Then you don't have to do any calculations. You don't have to take, VI plus is 3.1 volts and VI minus is 2.9 volts. Let's say the average, 3 volts. You don't have to do that if you tie them together. You already know the average. So let's look at, let's say you tie VI plus to VI minus. So this is VI plus equals VI minus equals, let's say 3 volts, since I already said that. And then you see that because you have the two inputs at the same value, their emitters are in this on the same node. So the emitters have the same voltage. Now the bases have the same voltage. The resistors are the same. So you should have the same current going through both sides. And V out plus should equal V out minus. Okay, let's say that's also 3 volts for some weird reason. So then on the homework, I see some people using a differential input. And let's say you started out, instead of setting VI plus equal to VI minus, let's say you had 3.1 and 2.9. What's your average? Just your 3. And then let's say I made 3.2 and 2.8. What's my average?
3.
Still 3. So you haven't changed the average. So be careful of that when you're trying to get the common mode gain. That doesn't change. Having a balanced input doesn't change the average. So you need to, if you're tying them together, you try 3 volts and then you try, hey, 3.1 volts. So let's do that. Let's change VI. I don't know why my pen decides not to work during class. Let's go to 3.1 volts. And let's say your V out plus equals your V out minus equals, let's say, 2.9 volts. Okay, then plugging it into this equation. It's back. Okay, good. CM. My first pair of values is my V out is 3 volts and my V in is 3 volts. So you have 3 volts out average. The average of the output's 3 volts and the average of the input's 3 volts. And then for your input, first one, for the second term, average of the output is 2.9 volts and the average of the input is 3.1 volts. So your ACM is 0.1 volts on top and negative 0.1 volts on the bottom, which equals a negative 1 gain. Do you think this is if you change the average of the inputs, do you want the average of the output to change?
No.
No. So is this a good ACM? What would be the ideal ACM?
0.
0. So ideal ACM equals 0. That means when the input averages change, the output doesn't change. So you'd have like 3 minus 3. Okay, so that's the ideal ACM. So this is not a great ACM right here. And this is a metric for differential circuits. So this is a metric for differential circuits. Okay, so that's the experimental way to find ACM. Any questions on that? I think we touched on it last time. So,
what's the difference of this and the ADM?
and the ADM?
Yeah.
Okay. ADM is so this is it's taking the average of the inputs, not the difference in the inputs. Mathematically, that's the biggest difference. So for ADM, remember this one, you're moving the inputs together. For ADM, they're equal and opposite. So that would be V out plus minus V out minus, and it's at some input. And then you'd change the difference, not the average of the inputs, but you change the difference between VI plus and VM minus. So
Okay.
you probably want to keep the average same for ADM. Oops, V out plus 2 minus V out minus 2. VI plus 2 minus VI minus 2. It doesn't look like a 2. Okay. 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 And for those in the other section, in the second section, we actually got to this derivation for the theoretical. In other words, the theoretical gain for a common emitter is minus GM times RO in parallel with R. So I already went through the math for that in the second section. So that's what I'll do next here. So that's if you're in the lab or you're using LT-SPICE and want to manually find ACM. Okay, so the theoretical ACM. Okay, again, do you remember the technique we used to find ADM, the theoretical ADM?
Half signal.
Half analysis. It does sound like a C, but so you're chopping the circuit in half, so it's called half circuit analysis. So for the differential mode for ADM, because the inputs move equal and opposite, we could call sorry, apparently there's something to bark at. So we could, this Vn right here, for differential mode, we were able to say that doesn't move. And then we could say, oh, if it doesn't move, then it's a virtual ground. And now I've got 2 common emitters, and you know the gain of a common emitter. But for ACM, that doesn't work. So again, let's do a quick, oh, there must be a siren coming by. Oh, Amani, how do you spell this again? A? Contradiction? My spelling help. Can you hear over the dogs?
Yeah.
Okay. All right, so I'm gonna try. Vn doesn't move. And this is proof by contradiction, so this is actually wrong. Doesn't move. Okay, so first I'm going to say, okay, Vn doesn't move. And let's say, just like in the last example, I'll say Vi plus equals Vi minus equals 3 volts. And then I move that to 3.1 volts. Okay, at 3 volts, there's going to be some VBE here. And if Vi plus equals Vi minus, and this is ISS, what's the current through each side here? What does it have to be?
Half of ISS.
Half of ISS. Okay. Okay, so that's when Vn plus and Vn minus equals 3 volts. Okay, so now when I move it to 3.1, and this is where we find the contradiction. Let's say Vn doesn't move. What happens to VBE? If I move Vn plus up, but Vn doesn't move, what happens to VBE?
It's smaller.
It get smaller or larger?
Vn is going up,
Yes.
doesn't it?
Vn.
I'm assuming it's getting bigger, but I don't know why.
Okay. Now, so Vn doesn't move, and Vn plus goes up.
Oh, okay, yeah.
So your VBE just increased. If VBE increases, what do you know about the current?
Current's gonna increase.
It's going to increase. So now this is trying to conduct ISS over to plus some current. And what's happening over here on this side? Assuming this.
Wait, by Vn plus, you just mean the Vn on the positive side?
Well, let's say just for convenience, usually when you're doing, anything common mode, you tie Vn plus to Vn minus. So whatever Vn plus is doing, Vn minus is also doing it.
Oh, okay. Okay, then I thought you were saying Vn. That's why I was confused. Okay, you're saying Vn. Okay.
Yeah, I'm sorry.
Okay.
My bad.
That makes more sense. Yeah, then wouldn't that current also increase?
Yes.
If Vn minus increase?
Exactly. So now you've got that. Do these sum to ISS now?
No.
No. So if you assume that Vn, should we call it Vx? We can call it Vx.
No. Okay.
So if Vn doesn't move, then when you change the averages of the input, they won't sum to ISS anymore. So Vn has to move. So okay. So that assumption that we did with the differential mode half circuit, where we said Vn doesn't move, so let's make it an AC ground, a virtual ground. We can't do that anymore. So we have to find some other way to do our half circuit analysis. And what I'm going to do is let's look at the tail current source. The tail current source is basically a transistor with, so if you're using a current mirror for your tail current source, that's basically a transistor with a bias voltage on it. And the bias voltage comes from that biasing circuitry, the resistor and the diode connected transistor. Okay, so my question is if I treat this as a resistor, what size resistor does it look like? Perceived resistance. And the first thing you should notice there is that I'm saying perceived resistance or small signal resistance. So that immediately should take you to small signal analysis. Okay, so let's do that up. EERO. And the emitter's grounded, so I'll ground that. This is the resistance I'm asking for. It's supposed to be R out. That's not very good. And what happens to the base?
It's grounded.
Okay, so anything drop out here?
From the current source.
Current source drops out.
And
So
our
this,
pi.
yeah, 0 volts across R pi, so that goes away. But now VBE 0, so that goes away. So what happens is this just goes to RO. So this tail current source, it basically acts like a resistor of size RO. So I'm going to redraw a slide down here. Sorry, I know people might still be writing. So I'm going to take our circuit, and instead of putting a current source there, now I know that I say when you're doing this right now, this is a mixture of large signal symbols and small signal values. So this is actually a really weird form right now. This RO is actually the small signal, the perceived resistance of that transistor on the bottom. And this other stuff is still voltages and currents. So it's kind of a mixture of small signal and large signal, and that's usually a really bad thing to do. But it's going to make our life kind of a little bit easier. I don't know what's going on with the doggy. So
Professor, so there's a transistor that's actually there instead of ITIL? Or, yeah.
yeah, this,
So there's a transistor that's creating ITIL? There?
yeah, if you see a current source symbol, you can assume that it, I don't know if you can like rolling around back there making weird noises. If you see a current source, that in a real circuit would be replaced with a current mirror.
Oh, right.
So this is just saying, let's take that one step. Let's let what's it called? De-abstract it and turn it into the actual circuitry that would go there.
Okay.
And that would be a transistor with the biasing circuitry. And this is a DC voltage right here. So okay. So we're down to here, and I'm going to do something here. My claim is that if I do this, nothing changed. So if you put two resistors in parallel that are the same size, it's just R over 2. So if I double the resistance and then put two of those in parallel, it goes back to the original resistance value. Okay, and we had this current coming through here. We had ISS over 2 coming through, ISS over 2. What can you say about the current through these two resistors down at the bottom? What can you say about the current going through the? Is that
It's just ISS over 2 through
exactly.
each of them?
Yes. So they still have ISS over 2 through each of them. Okay. And here's my final claim. If I can. So my final claim is that if I erase this, nothing changed.
It's true.
Okay, yeah, because these both have the same current going through them. So in theory, there's no current going through the branch that goes across. And remember, when we were testing this for common mode gain, what we were doing is we were tying Vn plus to Vn minus, and we were moving them. And so what we do is we tie Vn plus to Vn minus, and we move it up, and then we'd see what happened to V out and V out plus. But we also know that V out plus equals V out minus, just because inputs are the same, emitter down here is the same, resistors are the same. So if you tie Vn plus together and move them, V out plus and V out minus will move exactly the same too. Is that okay? Okay. So my claim is that now that I've cut this in half, I have two halves of the circuit. My claim is that I can just, since I know when I was looking at this whole circuit, I was setting Vn plus equal to Vn minus and watched how V out moved. My claim is that if we can find the gain of just this half of the circuit, it will give us our ACM. What do you think? Do you agree if I had both halves right here and I connected Vn plus to both inputs and I moved them together, the V out plus and V out minus would also move together? Would also do the same thing? Okay. Let's see. Okay. So whether you put it on both inputs and watch both outputs, I mean, both inputs and both outputs are doing the same thing, will give you the same result as if you just look at one side and see when I change Vn minus, how much V out plus moves. Or I could have picked this other side and said, when I move Vi plus, how much does V out minus move?
Okay.
Okay. Satisfied?
So
Let's
the
see.
fact that they're the fact that they're connected doesn't affect their total gain because the relationship between the pluses or the V outs and Vns are the same.
Yes.
Or like, yeah. Okay.
Well said.
Okay.
Okay. My claim is if I had that whole circuit all put together and I moved Vi plus together, V out plus and minus would move together. And they would move exactly the same amount as if I just had this half circuit here and I moved V in and watched what V out did.
Okay. That makes sense to me.
Okay. So on to the last step. So what is the circuit that I circled?
Common emitter with degeneration.
Common emitter with degeneration. Now, what size resistors did you use for degeneration in the lab?
Relatively small.
Relatively small. What's the value for RO? In this case, it's VA over IC. For our transistors, again, VA was like 100, and if we're having 1 milliamp, that is a 100 kilo ohm resistor. So this is a common emitter with degeneration, but degeneration is like 200 kilo ohms instead of 25 ohms like you've been using in lab. So massive degeneration. And let's go, it's not all going to fit, but Remember the update that I did to this handout for GM? If there's degeneration, I don't know if you can see this. If there's degeneration, then GM is not little gm anymore. GM is this equation. So let's see. Giving this a try. And maybe shrink it one. Okay. Oops. So just using the quick method, remember that AV equals big GM times big R out. Whoops. Okay. And for this circuit, what's R out approximately? Let's call this R. Well, let's just do GM first. What's the GM for a degenerated circuit? Got this over here. Okay, when there's degeneration, your GM is just your, this is a common emitter, so there's a minus sign. 1 plus GM RE. So that's your big GM. And then your R out. What's your R out for that?
RO in parallel with RC.
RO parallel with RC. And so if you look at this, if RE is, thousands, then GMRE is going to be, and this is not the greatest approximation, but GMRE is going to be much bigger than 1. So you get minus GM over GMRE. Let's make this prettier, sorry. So assuming that GMRE is much bigger than 1, then you just get minus GM over 1 plus GMRE, which is actually minus 1 over RE. And then if you put RO in parallel with RC, what probably happens?
Approximately to RC.
Yep. And in 346, you actually used this equation for your gain for one of your labs. At the end where they had the common emitter lab, and they just said, here's the gain, believe it. This is how they got there. They made this assumption, made these two assumptions, RO much bigger than RC. Okay. And in this case, what's your RE for our circuit?
2 RO.
Exactly.
Yeah.
So what is your gain approximately? Minus RC over 200K. What's your gain gonna? RC maybe is a few thousand. Let's make RC 5K. Just totally random, picked out of the air values. So don't think I did any high math to come up with that. I just picked a 5K. You do that. Should I make it 2K? Let's do that because that's better for my math brain. 2K. All right, so if you have 2K over 200K, what's your gain? That's pretty darn good. So you want your ACM to be very low. That means that you can have noise on both of your inputs. If it's the same noise, it just disappears, doesn't show up on the output. Okay, so important points here is we used the GM for a degenerated circuit to come up with our gain equation. Right here, big GM times your R out. The other thing is that this half circuit analysis, we ended up with a common emitter with degeneration, which gives us an equivalent gain to our ACM gain. Okay, good. Okay, questions on that? So if somebody asks for the theoretical gain of theoretical common mode gain, it's a common emitter with degeneration of 2RO.
So we want ACM to be small because, like you were saying, that means that if you have the same inputs or like around the same inputs, then your Vout will be around the same. And you are like, sorry, why did we like it low again?
Okay, so what often happens if you have a differential circuit, you have two signals coming in, and those signals generally, if they're routed well on a chip or they're routed well on a printed circuit board, or even if they're coming across the floor in the lab, they're going to be near each other. And so if they're near each other, they're going to see the same noise. So if it passes by, I don't know, the air conditioner or something, it'll have a spike. Both inputs will go in the same direction. And if you notice, that means their average is changing. So if you have the same noise on both of your inputs and your common mode gain is 0, that means it doesn't matter. Your output won't be affected at all. If the average of your input changes, like with this noise, the average of your output won't change, and it won't affect your output signals.
Thank you, Professor. That makes sense.
Okay. All right, so on to a couple more metrics. These are, again, they're trying to give you a bunch of information with just one number. And common mode rejection ratio. So this is common mode rejection ratio. Common mode rejection ratio. Any of these rejection ratio metrics, you want them to be gigantic. So any RR metric, want it large. So far we had ADM that we wanted big. We had ACM that we wanted small. The rejection ratios we want big. So we want this one small. Okay, and what the common mode rejection ratio is and again, also these rejection ratios are usually something you want, usually something you want big over something you want small. And for the gains, we've seen two gains. We've seen ADM and we've seen ACM. Which one do you like?
ADM. Is
ADM.
that the one we're supposed to like?
Yes, we like ADM. So that one goes on the top, and that's the one we want big. So that's good. And then which one do we hate? Not hate. That's a strong word. ACM. So if somebody brings you their circuit and they say, oh, my common mode rejection ratio is 10,000. That means that the ADM, the gain you want, is 10,000 times bigger than the gain you don't want. And that's pretty darn good. Yeah. Okay. Let's see. One more. I was hoping to get to one more thing today, but that's not going to happen. It's always so much shorter in my head. Okay, so I'll scroll this up. This is power supply rejection ratio. And this is, again, tells you something about the gain. And it's the gain you want, which is
ADM.
ADM, over a gain you don't want. And this particular gain is a weird one because it's not, doesn't have to do with the inputs to your circuit. It has to do with how much of the noise on, say, ground gets to the output or how much noise on the supply gets to the output. So this is gain from supply to output. And the gain can be, supply can be ground, or it can be VDD or VCC. So it's not the input signal, it's coming from some of the power, one of the power rails. And let's look at an example. So the common mode rejection ratio, that is something that you use with differential circuits. So let me write that down too. That was small, and it's for differential circuits. So common mode rejection ratio is only for differential circuits. This power supply rejection ratio can be used with differential or with single-ended input, single-ended output circuits. And let's use single-ended input, single-ended output circuit just as an example. So let's go down back to our power supply rejection ratio. And let's look at a common emitter. V in, V out. Okay, this time it's not ADM. Think of it more as the gain that you want. So what's the AV of the gain of a common emitter?
Negative GM, RO, and parallel with R.
Yes. Okay, so we've got that. That's the gain we want. That's going to go in the numerator. But now we need to say, let's do power supply rejection ratio. You have to pick one of the rails. You can't do it from both VDD and ground at the same time. You say, what's the power supply rejection ratio from VDD? And then a separate problem is power supply from ground. So let's do power supply from ground for this common emitter right now. So we're using a common emitter as our example. So what you do is you say, well, I just want to know what happens if there's noise on ground, how much of it shows up on the output. So I don't want the input to move anymore. So I'm going to and I'm going to erase in a minute. So don't draw the ground in. So that's our circuit, but I'm just going to put the bias voltage on here now. I'm not going to put any input signal on. I'm going to make the input nice and quiet. So I can, whatever I see on the output, I know that's coming from ground. And then what I do is, actually, let's do, I say, okay, now I want to know what happens to noise on ground, how much it shows up on the output. So I'm going to take ground. I'm going to take where ground was, and I'm going to change that to V in. So now I'm going to take this, and I'm going to delete it. And what was ground before, I'm going to change that to V in, because I want to see how much a moving signal on ground, noise on ground, how much of that gets to the output. Up to there, why I'm doing everything, is that okay?
Yeah.
Okay. All right, now looking, if I just showed you the circuit, what would you think the circuit was?
Common base.
Common base.
Oh wait, I always mess it up.
Oh no, you got it.
Oh, actually, yeah. Okay.
Yeah, exactly. So this is the gain of a common base, and using the quick method, you can use GM times R out. What's GM for a common base? Sorry if I moved that up too quickly. What's big GM for a common base? So first, is a common base inverting or non-inverting?
Inverting.
Common emitter is, and they look exactly the same. It's just the inputs switched. But the common base is actually not inverting. So your GM, just your GM, and because it's non-inverting, there's no minus sign. And then what about R out? What's R out of this circuit? Again, using the quick method is fine.
Is it just RO in parallel with big R?
Yep. So we've got that. So now we've got how much a signal, how much, not a signal, I shouldn't say a signal, how much noise on ground gets amplified and shows up on the output. Okay, and what you'd like to do is since you're trying to amplify the signal coming in on the input, you want this gain to be much bigger than the gain from ground, right? Let's see, our, oops, power supply rejection ratio for a common emitter from ground. We have our, usually it's absolute value, got a minus GM RO parallel R for the gain we want. And then we have the gain of a common base, which is GM RO parallel R, which is the gain we don't want. So we want the gain we want from the input to the output to be much bigger than the gain from ground or supply. But what is this? What's that equal?
Negative, or 1.
-1 with the absolute value around it, 1. And that's awful. That means any noise on ground gets amplified just as much as any noise on the any signal on the input. Okay. I know my time's up. Just one last question on this. When would you care about? When would you care about power supply rejection ratio? When's it important to have a good power supply rejection ratio? This isn't. I'm not sure if this is a technical problem. It's more a question about environment.
When your power supply is noisy or your grounding is not very good.
Exactly. So if you have a stupendous ground that's always nice and constant, you don't care about the power supply rejection ratio.
Yay, LDOs and star grounding.
Okay. Right. Right. That's what I've got for today. That's the other stuff I was going to talk about. Will show up on Wednesday, and it's actually I enjoy it. So look forward to Wednesday. Which is yes, off the shelf op amps. Oops.
Thank you, Professor.
All right. Bye.
Hi, Professor.
Yeah.
I was wondering if you said that the homework we could turn in on Wednesday.
Yes.
Okay. I was wondering because I have a pretty busy schedule this week.
Yeah.
Thank you so much.
Yeah. I'm not very good at. I'd rather people do the homework
Mm-hmm.
than just take off points. I don't like doing that. And I
Okay.
know so many people are busy this week, so.
Yeah. Okay. Thank you so much.
Sure. Zoom recording. Okay. We've got nine today. Ooh, big class. Okay. So that probably means that some of the stuff that I talked about last class, I probably should go over again. So how many of you were here when we went through the half circuit analysis, finding the theoretical gain of the differential pair? So when you got down here and you did this and did the resistor down here instead of the current source. So how many of you? Okay.
Oh, sorry. We got up to GM over 1 plus 2 GM RO times RO in parallel with R.
Okay.
I think that's about the last note we took last time for this section.
Okay. So how many of you went to a different section on Friday? Oh, all of you were here? Okay.
I didn't come, but I like watched like videos and stuff online.
Okay. You, me, and Bob should get together, Chaz, for when my hair actually gets. I can't compete with you, but
Wait, who's Bob?
Bob Intezar. He always ties his hair up real tight, but when he lets it go, it's just.
I will put hair back, but not today.
Oh, I actually tried to straighten my hair once, and only half of it straightened, and like this side stayed curly, and this side, yeah. And so I wore a hat until it grew out. But anyways, nothing to do with 308. So let's start from the top of the list. I updated what was the handout for week 5. Everything's going really slow on this computer. I'm a little worried. If it crashes, then I'll come back. Oh, now we've got. Okay, one more person joined us. So week 5 handout had this table that we came up with to help with the quick method. So it gave you, the resistance into a gate, to the drain, to the source, base, collector, emitter. emitter with a common collector Rn or a common emitter with degeneration, and all those other values. So that table we saw back like a week and a half ago. I added GM information. So for all circuits except those with degeneration, GM is just little gm. And if it's inverting, then it's minus little gm. If it's not inverting, then it's positive gm. And these are the 4 circuits that can have degeneration. So common collector is not one. You can have a common emitter with degeneration. We've seen that a few times, and you've seen it in lab. You can have a common source with degeneration. It's the exact same circuit as the common emitter with degeneration, except the BJT is replaced with a MOSFET. Or you can have a common base or common gate. And it's the same circuit, just like with when you go from common emitter to common base. For the common emitter, the input's on the base and the ground is an AC ground. When you go to the common base, the AC ground is on the base and now the input's on the emitter. So it just flips where the input and biasing is. And it's the same thing when you go from with degeneration. Wherever ground was, that becomes your input. And also for common gate with degeneration, that's you have V in below the resistor. Is that okay? All right. And if you have any one of these 4 circuits, again, degeneration, the GM isn't little gm anymore. It's actually little gm divided by 1 plus gm divided by, 1 plus gm times that degeneration resistance. And you can find this doing small signal analysis if you want. Okay, good up to there. So there's that addition to this handout. I reposted on week 7 with these updates in it. That, and then there was a request just to draw in all the vanilla single transistor amplifiers. And so I just added pictures of each of those. And so this will be helpful when you're doing the quick method. Okay, questions there? All good? Okay. If nothing, no questions there. So now we have 11 people. So I know that. So is there anybody that wasn't here on Friday for the second section? Oh, now we've got 12. So is there anyone that wasn't here on Friday that didn't look at the video? So is there anyone here that wasn't here on Friday that didn't watch the video? Really? Okay, then I'm going to go kind of quick. Right. So the first thing, since I was going to talk about ACM, I just wanted to refresh you on the experimental equation for it, and that's this ACM equals VOC. So VIC and VOC are the averages of the input for VIC, and the average of the output, that's VOC. So since you're working with averages, it makes the math just so much easier if you tie Vn plus to Vn minus. And now they both have the same value. Now you know the average is just whatever value they are. Okay, and then when you change VIC, then you just move VI plus, which equals VI minus, move them up kind of together. And then you observe V out, and V out, even though it's not tied together, both the left and right side are exactly the same. The transistors are the same, the resistors are the same, the base voltages are the same, and then the emitters are tied together. So the emitter voltages are tied together. So the left side and the right side, they're identical. So if you move V in plus together, the V outs will also be equal to each other. And that's the easiest way, whenever you hear common mode anything, the easiest way to measure something is to tie the input and output together. Sorry, the VI plus to VI minus. And then the outputs will move together. Okay, so I think we went through this. This is an example where we start out with VI plus equals VI minus equal to 3 volts. And that will give us some value of V out. I just randomly picked 3 volts. This has nothing to do with any numbers I gave you or anything else. Okay. And then if you change the VI plus equal to VI minus to 3.1 volts, V out, both plus and minus will move together because both sides are identical now, and you might get a new value. And if you plug those values in, what's the average of the inputs for this first case?
3 volts.
3 volts. So that goes here. And then what's the average of the output?
3 volts.
3 volts. And then you change the average of the input. Actually, I moved it up to 3.1. So now you have the average of the inputs, 3.1. And you look at the average of the output, which is 2.9. And this gives you an ACM of -1. And do you think that's good? Is that a good one?
No.
No. It says however much the average of the input changes, that's how much the average of the output changes. So if there's noise on both inputs, your output is also going to be moving like this. What's an ideal common mode gain?
0.
0. So the average of the output, even though the inputs are moving around like this, you'd like the output just to be flat, not moving. Okay, so that's that. This is a metric for differential circuits. You have to average between two values, so you need two inputs. Again, anything on here, I'm going fast. So anybody that has a question, please stop me. Okay. All right, and then there was a question in the last class, how's that different from ADM? And the biggest difference is that each one of these terms in the ACM gain equation, those are averages, whereas these are differences. You want to know the difference between VI plus and VI minus, not the average. Okay, so here's a question for you. Let's say you have a balanced input, VI plus equals VI minus, and let's say you're trying to find the common mode gain. If I move VI plus up 0.1 and VI minus down 0.1, let's say to 3.1 and 2.9, what's my average?
3.
Okay, and then let's say I move this up to 3.2 and this down to 2.8. What's my average?
3.
3. Can I use that to find the common mode gain? Those 2 points?
No, because they both have the same average.
Yes, you're working with averages. So even though both signals move, they could move by a lot. If the average doesn't change, this VIC1 will equal VIC2, and you'll get infinity or 0 something. Infinity, I guess. Okay, does that 3.1 and 2.9 and 3.2 and 2.8, does that work for the differentials, the ADM gain?
Yeah, but you would just, there'd be just a gain of 1, wouldn't it?
I didn't tell you what the output change is, but
Hmm.
you're right on the if I go from you can't really say for the gain until you know the outputs, but I know what you mean. But right here you have 3.1 and 2.9, so you've got 0.2 because that's a difference. And then if you go to 3.2 and 2.8, now it's 0.4. So the differential value did change, but the common mode value didn't change. Okay, so what about, let's say I do 3.1 and 3.1 on the inputs, and then I go to 3.2 and 3.2. So I change both VI plus and VI minus. If I go up by 0.1, does that work with the differential for ADM? No, why not?
Now you'll have 0 in the, well, like mathematically, you'll have 0 in the denominator, which,
Yeah, the difference, it's the difference has to change. And did the difference change when I was at 3.1 and 3.1 and then 3.2 and 3.2? Yeah, so the difference has to change there. Has to, the space, the voltage between the plus and the minus has to change for the differential. But is this, can you use this for the common mode gain where it goes from 3.1 to 3.2?
yes.
Yes, because the average is changing. So questions? Oh, okay. All right, so that's that. And then we did half circuit analysis. I'm just worried that somebody here probably hasn't seen that derivation. Okay, I'm gonna keep going. Nobody's raising their hands for not having seen this. But when we did the half circuit analysis for ADM, so this is, let's put, where's my pen? Not writing. So this is ADM experimental, the theoretical ADM. We found by doing half circuit analysis, and that was your GM RO parallel R. Okay, so this is if you're working it out on paper, and this is if you're in LT Spice or you're in the lab, or you take points and calculate it that way. So this is theoretical, this is experimental. Okay, so we have the experimental, let's write experimental here. We have the experimental equation. So for, again, for LT Spice or in the lab, we need the theoretical equation for a diff pair, ACM. Okay, I'll try one more time. Has anybody not seen this, the half circuit analysis? Otherwise, I'll go near the end of it. Okay, so one thing that we did here that, because I was trying to save a few minutes, is we looked at the tail current source. So in class last time, I just said, oh, this is, you can replace the tail current source with a resistor of size RO because, hey, that's what the collector sees. But to do that a little more rigorously, a tail current source is going to be a current mirror or a really big resistor, but usually a current mirror just because that's generally the better way to do it. So if you look at a current mirror, this current source symbol right here, that whole thing is going to be this whole thing. And you're going to have this current, this ISS. It's going to be a current mirror that you use for that current source. It's the base voltage here. That's V bias. If that's DC, what do you get to do to it in small signal analysis?
Treat it like a ground.
Treat it like a ground. So we're trying to find the perceived resistance on this node. So we treat that like a ground. That means you can ground it. If you ground it, the emitter's grounded, so that's grounded right here. So voltage across R pi.
0,
0. So your VBE is
0,
so your current source is
gone.
gone, and you just end up with RO. So last time I just kind of quickly said, oh, let's replace this with RO, but it actually makes sense if you go through the derivation and assume that's a current source. Okay, so the next thing, just to remind you of what else went on with that derivation, is we looked at this node, and for the differential mode gain half circuit analysis, we assumed that this node didn't move. So when the inputs are equal and opposite, Vn doesn't move. But we did a kind of a proof by contradiction that if Vn plus and Vn minus both go up, that node has to follow to keep ISS over 2 on both sides. If this node down here doesn't follow and you move Vn plus up, now this is going to conduct more current, and they're not going to sum to ISS anymore. So Vn moves just about the same amount as Vi plus and Vi minus. Okay. So now this node, we've decided this node doesn't move anymore, or it does move, has to move. And we went down, we said, okay, we know that the tail current source is going to behave like a resistor of size RO. And again, stop me if I'm going too fast. RO. So we can, what we did here first is said, okay, so we know the tail current source behaves like a resistor of size RO. And we said, well, I claim this is true. What I just erased, I claimed that it's still, when you put two resistors of size twice the size in parallel, then it comes back to just RO for the perceived resistance. And then I said, okay, if that's true, then I can just erase this connection, and both sides, since they're totally symmetric, that will behave just like if you had your original circuit and moved Vn plus and Vn minus together. Okay, I think that's where we got to, and then I rushed off kind of at the end a little bit, but up to there, any questions? I know it's really hard to ask questions because I just went about 400 miles per hour, but. Oh, nodding, thumbs up. Okay, right. So then we got over here and we said, okay, in real life, I'd be moving Vi plus and Vi minus together, but now they're separated. So if I just move Vi plus on, or Vi minus on this side and watch what happens to Vi out plus, that will give me the same results as if I move both Vn plus and Vn minus up or down and watched V out plus and minus on the original circuit. Okay, so then we said, okay, so first question, in lab, what size resistors did you use for degeneration?
I didn't use degeneration resistors for my lab, just
Okay.
so I'm not sure.
Okay. What about if you did? What kind of sizes did you use?
They're pretty small, right? I think I did like 75.
Okay, 75. This is, what's this circuit? If you had to name it, what would you name it?
Common emitter with degeneration.
Yes. And I just did, again, I used the VA equals 100, and I used 1 milliamp, and that gives you 100 kiloohms for RO. So this right here is a common emitter with degeneration of 200 kiloohms. So how much gain do you think this is going to have?
Not a lot.
A lot.
Exactly. So let's look at exactly how much. So this has degeneration of 200,000 ohms. Let's go back to the addition to this handout for GM. This is degenerated, a degenerated common emitter. So if you, again, the gain is going to be big GM times R out. What's R out of this common emitter, approximately?
Would it be R out in parallel, or excuse me, the R, I guess, in parallel with RO? Would it be plus 2 RO, or do you not follow all the way down?
I get lazy. I just say, hey, it's bigger than RO and be done with it. For the quick method. You can already tell whether it's going to be big or not. Okay, so you have RO in parallel with R. Call this R. RO in parallel with R. And then the GM can get from this addition. I don't know if you can see it here. So your degeneration, so GM with degeneration, it changes. And this is your new GM right here. So what you have is, let's see if I wrote it down below. Looks like this might have been when my pen was not working. GM R out, and you know R out's RO in parallel with R, at least. And then GM is that GM over 1 plus GM comes from here. And again, you can prove that to yourself by doing small signal analysis. And so, and it's a minus sign. Why is it a minus sign?
Because it inverts.
It inverts. It's a common. It's still a common emitter. So you have negative GM over 1 plus GM RE times your RO parallel with RC, and that's your gain. And then if you assume that GM times RE is much bigger than 1, what's this simplified to?
Could you ask that again?
Okay, so you have minus GM over 1 plus GM RE. And if GM RE is much bigger than 1, what's the denominator turn into, approximately?
Just GM times RE.
GM times RE. So now you have minus GM over GM RE. GMs can cancel out, and you get minus 1 over RE. Okay, what about RO in parallel with RC, if RO is much bigger than RC?
Just RC.
RC. So you may have seen this equation in 347. It just showed up in the lab manual, and they said, oh, the gain for this circuit is RC, minus RC over RE, but didn't tell you where it came from. This is where it came from. Okay. And then the final step here is your RE. If you come back up here, your RE is actually 2RO. So if this is going to be, I just randomly picked a number here. I said, let's make it 2 kilo ohm. If RC is 2 kilo ohm and RE is 2RO, and you can assume VA equals 101 milliamps, so it's 100K. This is 200K. And 2K. So your gain actually is minus 0.01. And remember, what we're trying to find here is the common mode gain. In other words, when I move the VI plus equals VI minus, if I move the inputs up 1 volt, the output moves by 0.01 volt, 10 millivolts. Okay, so that is where kind of the goal to get to was today. Questions there on common mode gain?
So does that make it, I mean, 0.01 is a pretty ideal common mode gain then, because
Mhm.
like you mentioned last week, if it's just noise coming in and you need a whole volt just to make it move 0.01, it's essentially not moving at all.
Mhm.
Okay.
This is really good. And if you use an active load, things change here because now your RC is RO. And so this gets worse. And you'll see on the homework, when you get experimental results, that it won't be 1, but it will be like minus 0.7 or something like that. It won't be this good. Okay, so just on to just a couple more metrics. I think we can get to something I think is funny. I think is fun. Not everyone does, but I think we can get there. Let's just go through a couple more metrics here. Okay, so common mode rejection ratio. There's 2 metrics that you see on data sheets and show up in other classes too. One is called common mode rejection ratio, and whenever you see the words rejection ratio, that is something that you don't like. So it means, or sorry, it's let me say this, let me just do what I wrote here. So any rejection ratio metric, you want it to be large, and it's, I would say always, but I don't know if there's some metrics that I don't know. So I said usually, but that, really in my brain, it's always. It's something you want big over something you want small. And common mode rejection ratio, it's one of these metrics where it's like gain. So if I come up to you and I say the gain of this amplifier is 20, that already gives you a bunch of information about that amplifier. If I could say, another thing I could say is I could come up to you and say, when I change my input by 0.1 volts, I get 2 volt change in my output. That's the same as saying my gain is 20. And it's much more succinct, and everybody knows what it means. So these metrics are a way to give a lot of information to somebody with just one number. And so this common mode rejection ratio tells you about the gain that you want over the gain you don't want. So this is the ADM is that differential gain, and that's the gain that you're actually trying to get out of this circuit. For if it was a common emitter, it would be AV. All the gains that we've looked at up to now, that we wanted that gain. We wanted that gain to be big. So ADM is that differential mode gain, and we like it. And then ACM is the gain that we just saw, and that it is pretty small. Let's say made up numbers, I'll write made up numbers after I write this, but we know this is negative 0.01 from our last example. And if we have an RC of 2K and a GM of like, if we have our 25.9, our VT is 25.9 millivolts, and you divide that by 1 milliamp, then you get 25.9 times 2K. This thing right here would be, what would it be? Like 5K, 5,000 or something? Am I off by a digit?
I don't think so.
Okay, we'll put approximately, because it would, what would it be? It would be 180 or something. Tell me how bad my math is. Because that goes to 50, that goes to 1. Yeah, I think that's right. Should I just cheat? Okay, right, 9 times 2 equals. Oh wait, it's much more than that, isn't it?
But that's 25.9 milliamps, right?
But it's over 1, so it's 25.9 millivolts over 1 milliamp.
Oh,
So
yeah,
the
yeah,
millis
yeah.
cancel out. So then I multiply this by another 100. Wow, okay.
Yeah, that was what I was thinking. I was like,
Okay, 3 more zeros. And I'll fix this up. I'll put notes down here, just all the assumptions that I made in random number generation I did. Okay, yeah, so that's pretty big. That's pretty awesome. But yeah, so this is the gain you want over the gain you don't want. You want the gain you want to be so much bigger than the gain you don't want that it totally obliterates the gain that you don't want, totally hides it. And this does a pretty good job of that. Okay, so thumbs up? Okay, okay, one more metric, then we'll go on. Power supply rejection ratio. Again, it's a rejection ratio, so it's something you want big over something you don't like, over something you want small. And power supply rejection ratio is you have the gain from the input to the output. That's the thing you want. So that goes in the numerator. And then in the denominator, you are saying, when we talk about supply, I mean either ground or VCC, VDD. So it's one of the power rails. Okay. So what is on the denominator is if there's noise on the ground, how much shows up on the output. So let's say there's like a 1 millivolt ripple in ground. How much does that get multiplied by and show up on the output? So if you're doing the previous metrics have all been for differential circuits like diff pairs. This one you can do with single-ended input, single-ended output amplifiers and diff pairs. But let's look at, just because the math is easier, the example is easier to use a single-ended input, single-ended output circuit. Let's use a common emitter. Okay, and the denominator will make sense in a minute. Okay, So the gain of the common emitter, seen that a bunch of times. That's this right here. Okay, so that's the gain you want. That's your numerator. Now you want to see if there's noise on, power supply rejection ratio, it's either from the ground to the output or from the supply to the output. There's no power supply rejection ratio that goes from both the ground and the supply at the same time. So you either have to pick your power supply rejection ratio as coming from ground or power supply rejection ratio coming from the supply. So this one, I picked ground. So here's my common emitter. I'm saying if there's noise on ground, how much shows up on the output. Okay. And to be able to see that, I don't want the input moving anymore. So I have to put a DC voltage on the input. And now any change in the output, since the input's not moving anymore, we know it's coming from our noise source. Okay. So what you do is you take this, you put a DC voltage on the base, and then you say, okay, I'm going to put a little moving signal on ground and see how much shows up on the output. Okay, up to there, good. Okay, got a nod. Okay, so now that I've changed this around, I put DC on the input and I've put like a noise source where the ground used to be. What kind of circuit does this look like?
Common base.
Common base. And do you remember the gain for a common base? What's R out approximately? Using the quick method.
RO in parallel with R.
Perfect. Okay, and what's GM? Big GM.
Just little GM?
Exactly. And is there a minus sign or not?
No.
No, because it's a non-inverting amplifier. So you have the gain of the common base. Okay, but this gain is actually if ground moved, how much would that signal be amplified and show up on the output? So going back over to your power supply rejection ratio for a common emitter from ground, the gain that you want is minus GM RO parallel with R. That's your common emitter gain from the input to the output. And then how much a signal on ground gets multiplied and shows up on the output is just the gain of a common base. And that's GM RO parallel with R. And that equals
1.
1. So signals on ground get amplified just as much as signals on your input. Is that a good thing? No. So that's pretty bad. That's an awful power supply rejection ratio. We can go one more step here, or we can go the other thing. What about if we save the other thing? That'll help synchronize the previous section with your section. So let's look at power supply rejection for I have no idea what any of the buttons on this thing do, but when I push them in the right order for long enough, sometimes the pen comes back. Nope. Okay. So power supply, whoops, I already made an R, so we'll make that R. Power supply rejection ratio for a common emitter from VCC. So got this. Okay, so if you want the power supply rejection ratio, the denominator is the gain you want. So what's that?
negative GM times RO in parallel with R.
Exactly. RO parallel with R. Okay. And now, so now we've done normal operation. How do I prepare this circuit to look at the gain from, since I'm going from VCC now, how do I prepare this circuit to observe the gain from VCC? Weird way to ask the question, but
Bias VN.
bias VN, so you don't want VN moving anymore. So change that to V bias. Okay. And now, if what, and then what? Where's VN on your new circuit?
VCC.
VCC. So this now becomes VN. And this is a little bit weird because it doesn't look like any of the amplifiers that you saw. So now you kind of have to reason it out. It's not one of the amplifiers you know. So the question is, how much does V out move when V in moves?
Just R, right? Or I'm not sure.
Okay. What's, if you had an equation for V out, what would it be? Ah, darn it. No, still the mouse. V out equals, if you had to write an equation.
V in minus ICR.
Okay, so V in minus IC times R. And so how much does V out move when V in moves?
It moves by ICR.
Okay, let's say V in moved by 0.1 volt.
Does it move the same?
They move the same. Yeah, because it's this transistor that determines the current. So you've got IC going through your resistor. Got IC going through your resistor. If the supply changes, that just moves V out the same amount. So what is the gain from V in to V out?
Is it just one?
Exactly. Yeah. So if V in moves by 0.1, V out moves by 0.1. And remember, it's the delta over the delta, so it would be 0.1 over 0.1. And now, if you, it's already written up here. So now your gain is 1. So now your power supply rejection ratio is just GM RO parallel with R, which is much better than the one you, the one you got up here.
I have a question.
Uh-huh.
So that when you have at the bottom, we could use that as just a voltage follower or voltage buffer between circuits?
You could, but yes, you could.
Gotcha.
Good question. Interesting question. Okay. So those are all the metrics. Now I think I'm finally over with diff pairs. Let's keep quizzing you a little bit. I didn't do this with the previous class. Let's say let's just look at the diff pair on its own. How would let's say I wanted to have more gain in my input stage. So here's my diff pair. if I wanted to have more gain, what can I do?
Use cascoded, like make it cascoded instead of having a passive load.
Okay, yes, so you cascode both the Vn plus and the Vn minus transistor, and you replace these resistors with cascoded. What's in between cascoded and passive load?
An active load?
Active load. Okay, so you've got this passive load. This is the lowest gain. Then you could replace it with an active load. That increased the gain. You can cascode everything. And that actually has a special name when you cascode a diff pair. It's called a telescopic op amp because it kind of looks like a telescope. You've got the tail current source and then it goes out forever. And then what if you wanted super duper awesome, amazing gain?
Gain boost it.
Gain boost it. Okay, so there's 4 flavors of this amplifier. This right there. Okay, so I think this is a good spot to finish. Do you have any questions?
Would you be able to scroll back to the bottom with what you just wrote again, please?
Okay, for the VCC or for the from ground?
Yeah, for the VCC one. Thank you.
Okay.
My pen also stopped working, so I have to screenshot it.
Yeah, I replaced the batteries. I just don't know what to.
Well,
why
actually, I
it
guess
stops.
my touch screen is what is not working right now for some reason, so I don't know. But your pen, that's really weird that it just stops working randomly. Does your touchscreen work when you do your finger on it and stuff? Weird.
And this one, oh, now it's working. I will check. Next time I'll check that. That's a good thing to test. Okay.
Okay, thank you. Have a nice day.
Okay. See you later.